this module, you will learn about LC oscillations. The phenomenon of LC oscillations can be observed when a charged capacitor is placed in series with an inductor in a circuit. Consider a fully charged capacitor with plate A charged positively and plate B charged negatively, connected to an ideal inductor of inductance L. When the circuit is closed, the capacitor starts discharging through the inductor and discharges as long as a potential difference exists between the two capacitor plates. The current in the circuit is from A to B through the inductor. The potential difference across the capacitor is equal to that across the inductor. Gradually, the capacitor discharges and the potential difference between the plates as well as that across the inductor becomes zero. During the time interval, when the potential difference reduces from maximum to minimum, there is an induced EMF, which opposes the passing current in the inductor. Now, the magnetic field around the inductor starts decreasing, and this induces a current from B to A in the circuit according to Lenz's law. This induced current in the circuit, which is from plate B to plate A, charges the capacitor in the opposite sense, with plate B now positive and plate A negative. This induced current exists as long as the magnetic field exists around the inductor. By the time the magnetic field reduces to zero, the capacitor becomes fully charged. The capacitor again starts discharging, but now the current in the circuit is from plate B to plate A. This builds up the magnetic field in the inductor, but this time the polarity is reversed. Gradually, the capacitor discharges fully, and the magnetic field around the conductor grows to its strongest. Again, the magnetic field around the inductor starts decreasing, this time inducing a current in the opposite direction. This occurs until the magnetic field exists around the inductor. By this time, however, the capacitor returns to its original, fully charged state, with plate A positively charged and plate B negatively charged. Thus, we observe that the capacitor's charging and discharging is oscillatory in nature. Now, let us obtain an expression for the natural frequency of these oscillations in the LC circuit. Let Qm denote the maximum charge on the capacitor at time t equal to 0. At this instance, the current in the circuit and the induced EMF across the inductor are equal to 0. If Q is the charge on the capacitor and I is the current in the circuit at a time t, then the potential difference across the capacitor is the ratio of Q to C, where C is its capacitance. The induced EMF across the inductor is L di by dt. By applying Kirchhoff's law for the circuit, we get Q by C minus L di by dt is equal to 0. Let this be equation 1. As the charge Q on the capacitor decreases, the current in the circuit dQ by dt becomes negative. Equation 1 now becomes Q by C minus LD by dt of minus dQ by dt is equal to 0. This can be written as d square q by dt square plus q by LC is equal to 0. Let this be equation 2. We learnt earlier that the equation of motion for a particle of mass m in simple harmonic motion along the x-axis with a natural angular frequency omega naught is d square x by dt square plus omega naught square x is equal to 0. Let this be equation 3. Here, the natural angular frequency omega naught is equal to the square root of k by m, where k is the force constant for simple harmonic motion. Equation 2 is observed to be similar to equation 3. Comparing equations 2 and 3, we have the natural frequency omega naught of LC oscillations in the circuit equal to 1 by square root of LC. We know that in equation 3, the displacement x is expressed as a cos omega naught t plus phi, where phi is the phase difference and a is the amplitude of oscillations. Similarly, for equation 2, the charge q can be expressed as q is equal to qm cos omega naught t plus phi, where qm is the maximum charge on the capacitor. Let this be equation 4. At time t equal to 0, the charge q on the capacitor has the maximum value, qm, which means that the value of the cos phi has to be 1, and hence phi has to be 0. Hence, equation 4 now becomes q is equal to qm cos omega naught t. Let this be equation 5. As the capacitor gets discharged with time, we get current I is equal to minus dq by dt. Substituting the expression for charge from equation 5 and simplifying, we get I is equal to Im sin omega naught t, where Im is equal to omega naught into qm. Let this be equation 6. Now let us analyze the LC oscillations from an energy point of view. At any instance, the energy stored in the capacitor U is equal to Q square by 2C, and the energy stored in the inductor U dash is equal to half Li square. From our previous analysis, we know that at any given time t, the charge Q is equal to Qm cos omega naught t. The current I is equal to Im sin omega naught t, where Im is equal to omega naught Qm, and omega naught is equal to the square root of 1 by Lc. Rearranging omega naught in the expression, we get L is equal to 1 by omega naught square C. The total energy, U total of the circuit, is the sum of the energy stored in the capacitor and the energy stored in the inductor. Thus, U total is equal to Q square by 2C plus half Li square. Substituting the values of I and Q in this expression and simplifying, we get U total is equal to Qm square by 2C. This expression of total energy is equal to the energy stored in the capacitor when it is fully charged, which was the initial stage. Thus, the total energy in an LC circuit is always a constant. This also holds good as no external force acts on the system. Hence, this oscillation is self-sustained. We also observe that LC oscillations are very similar to the mechanical oscillations of a body in simple harmonic motion. In the case of a spring, when the spring is initially in an elongated position, all the energy of the system is in the form of potential energy. When the spring is released and it reaches the mean position, this potential energy in the system is converted completely into kinetic energy. When the spring goes to the other extreme, the kinetic energy in the system is again converted back into potential energy for the spring. In a similar manner, in LC oscillations, the energy oscillates between the electric field due to the capacitor and magnetic field due to the inductor. These LC oscillations sustain infinitely if all the elements in the circuit are ideal in nature. That is, the inductor has zero resistance and the capacitor is characterized by a single constant value called capacitance. However, in a practical situation, this is not true. Actually, the inductor also has some resistance, which leads to the damping of these oscillations. Similarly, neglecting the radiations emitted by the system also renders this analysis quite unrealistic. From our discussion of LC oscillations, we can draw the following analogies between a mechanical and an electrical system. We see that the inductance L is similar to mass. The value of 1 by C is similar to force constant K. Force constant K is the restoring force per unit displacement, whereas 1 by C is the value of the potential difference required to store unit charge. Charge Q is analogous to displacement x, which implies current I is analogous to velocity v. The total energy in both systems remains constant or is conserved. The effect of damping on the LC oscillations can be compared to that of a simple harmonic oscillator. You have now reached the end of this module. In this module, you learnt that the phenomenon of LC oscillations can be observed when a charged capacitor is placed in series with an inductor in a circuit. In an LC oscillator, the charging and discharging of a capacitor is oscillatory in nature. For an LC oscillation, Q is equal to Qm cos omega naught t and I is equal to Im sin omega naught t, where Im is equal to omega naught into Qm. Q is the instantaneous charge on the capacitor. I is the instantaneous current in the circuit. Qm is the maximum charge on the capacitor in a steady state. Omega naught is the angular frequency. T is the time. The total energy in an LC circuit is always a constant. U total is equal to Qm square by 2C.